All right, let's get started. This is way bigger than I thought it would be. Let's make it a reasonable size. Okay. So what are we looking at today? We're going to look at image dithering. And one reason why I thought I'll look at this is because it's just to do with subjective notional view of what is better for the human eye. So dithering is the process of intentionally adding noise to an image. The natural question is, why would you want to do that? And normally it's because you want to do some kind of lossy compression. You want to lower the number of colors an image uses. And that comes at a cost of course, some error. And then on top of that, once you've lowered the type of colors that you've done, and there's some very obvious and naive ways of doing it, you want to make it more aesthetically pleasing to the human eye, or perhaps you want to encode some of the missing information in some way or another. There's some examples on the Wikipedia page here. I think there should be. Here we go. To do with the cat. And there's also some other ones to do with the statue of David, I believe, and you can see the different kind of approaches. And in this video, or in this live stream, we're really going to look at the error diffusion dithering. More specifically, we're going to look at the floyd-steinberg algorithm, and I'm going to implement it here, and also the Atkinson algorithm. And then off the back of that, we'll look at some problems with using it in a naive kind of way, and it will be kind of obvious why they chose black and white in this particular example. Maybe at some other point in time I'll look at some other approaches like the ordered dithering, because I think some of it actually looks quite cool, like this one. These two look pretty cool, and halftone also seems pretty interesting as well. So let's get started. What we're going to do is I've loaded up an image of a parrot, and as I said, I'm going to do it in color, and I think this is a red velvet macaw, actually, macaw, however you pronounce it. And the choice of the color is so that you have some really high contrast, and it will become apparent why we want to choose high contrast as well. So if you go on scikit-learn on the webpage, in this link over here, you will be able to actually see an approach of how we can actually do some kind of lossy compression via k-means. And what I'm going to do here is I'm going to look at two kind of approaches of this kind of lossy compression. One of them is using k-means, and the other one is using a quantized palette, some palette that we've predefined. So just to understand this, and I'm going to run this code, right? And it's going to take a while because my computer is not particularly fast. When you look at the quantized palette, what does this actually do? This produces a palette according to how I've split it. So because I've done num splits, or n splits is equal to 2, it will generate 8 points, which represents a cube. And I think you can look at, I'm going to quickly bring it up, the 3-bit RGB palette. Well, there's a Wikipedia page that will actually talk through what I've done here, and just to show you what this palette looks like, I have here. So keep in mind that we have squashed everything to between 0 and 1 rather than 0 and 256 or 255 more specifically. And yeah, And you would also be able to see that this is where I got the parrot from. So if you choose the this is not the page I'm looking for actually, sorry. It's this one. It does actually show you what I'm doing with the cube. So I've picked a number of points between 0 and 1 to be 2, so it just picks all the corners. So it's visualized here within this Wikipedia article somewhere, if I scroll down far enough. So this is the 6-bit RGB, but if I chose a 2-bit RGB, it would just be the corners of a cube, which of course there are 8 of them, which is why there are 8. No. How do I get to that screen? Which is why there are 8 points which represent the corners of a cube. Alright, so this is a quantized palette, so we're going to choose 2 approaches. One of them is to use this quantized palette, which is to pick which color is most similar to the 8 corners of the 3D space. And also a k-means approach, which is to select or create or find 8 points that are sufficiently far enough, or creating some kind of clustering from each other that represent the image. Okay. So a lot of this code is just lifted straight from scikit-learn, so there's not much need to actually go through what the code is doing. I have it here. We can see on the left, this is the original image. The one in the middle is k-means, and on the one on the right is the quantized one. Now there's a few things that come to mind immediately. So part of the challenge of k-means is because, well, you just take the mean, it ends up just blurring all the colors together. So you lose that beautiful yellow that is in this particular screen, in this particular picture. On the quantized perspective, because everything is just on the 8 corners of this cube, you lose a lot of detail in for example the dark patches, right? It just turns all into black. And also it introduces this new color, this cyan, that just didn't exist in the original one, that depicts the color of the particular tree branch that the bird is perched on. So there again, you can see like the challenges with both of these approaches. Like this one seems just much more vibrant and greater contrast because the palette itself has a greater contrast. It's just the corners of a cube, whereas the one in the middle matches a lot closer to the original image, but is just a lot more muted, if you like. So what does the dithering algorithm offer? So dithering just says that we want to spread the error that is in images around. It doesn't say anything about increasing the palettes, but maybe you can get some detail that has just been smoothed out in these images that dithering can offer. But dithering doesn't just solve everything, because there are some issues, and we will see them very apparently when we start to implement it. So let's go ahead and try to implement. Okay. But firstly, before we do that, we need to talk through what the various approaches are. So I am going to add Pinson. There's the classical approach, I suppose, is the floyd-steinberg approach, where you go from and you scan the image from top left to bottom right, so all the way through the image, and you go and move the error as such. So if asterisk is the pixel on the right gets 7/16 of the error, this pixel gets 3/16, 5/16, and 1/16. So if you add all of these up, you get a total of 1, right? That's important. And for the Atkinson one, it's spread out in this way. And what is important for the Atkinson one is you'll notice that if you add all of the numbers up, they don't equal 8. So 1, 2, 3, 4, 5, 6. So what happens here is not all the error is spread to all the neighboring pixels. That's really important. The other thing that I need to stress again is that this algorithm goes from top left to bottom right. Okay, so a single pixel may have multiple passes through it, and is also sequential. It's not really can be parallelized in a naive fashion. At least there are ways to parallelize it. If you go online, you'll be able to see some approaches. But yeah, it's definitely not created for the purpose of being easily parallelized in a naive kind of way. Actually, what I'm going to do is I am going to use a small version of the original image, just so that this will run faster. Parrot small. So call it parrot small. Yep. See that it's much smaller. It's a lot more blurry, but hopefully it will run a lot quicker. You can see a lot of detail has been lost already, but we should be able to recover or be able to understand better what dithering does. In fact, it looks like a very cheap kind of color palette from the 90s or something like that. Let's go to implementing. So as I said, you go from the top left to the bottom right, and you iterate through it in order to process each pixel. Now, I've just ignored all of this at the top because this is just from the scikit-learn, but let's review it very, very briefly, what's going on. So for the k-means algorithm, how it works is it fits k-means to this image array sample. What is this image array sample? If we go up to this line, we can see that it's moved everything to be reshaped to be all the pixels are flattened out, so we lose a concept of where they are in images. Instead, they're all just stacked all in one massive line, right? So that's what's happened here, and this becomes the data set that we learn from, where D is the columns and this is the number of instances with times height. Okay, and then k-means is applied. In the recreate image, which is the important bit, we take this codebook and labels and the width and the height. So what is codebook? The codebook, it represents the centers within k-means, or the corners of the quantized color palette. The labels is the prediction of each individual pixel for which class it belongs to, and then this code just iterates through the whole image and updates all the pixels. So it initializes an image that is all zeros, and then it just iterates through all of the pixels and updates each pixel one by one. All right, and then returns an image. Okay, so how could we implement this in the floyd-steinberg kind of sense? So let's just define what this is, Steinberg. Right, and we have the original image, codebook, labels, WH. So already the signature I'm going to use is very similar to the recreate image, except I'm adding the original image, and there's a reason for that, because I'm going to call this image just to be very clear. Original, why not? And the reason for that is we want to diffuse the error into the image. So let's just copy this in case I overwrite it. It's important because we are going to iterate through base image. Okay, we're going to iterate through base image and update every single pixel by diffusing the error through it. And then the next thing we need is we need the actual recreated image of this codebook and label. So I'm going to call this the quantized image, or the, I guess the, yeah, I'm going to call it quantized image, right, which is just recreate image of codebook and labels UNH. And then we need to calculate the error. So the error is simply the base image minus quant image, sorry. So from here, we just want to iterate through the whole image to get to just create a new particular image. So let's go and have a go at that. Well, we're going to just copy and paste the code. It's already done. We're going to initialize a new image that is all zeros, and then we're going to iterate through all of the pixels. Okay. So let's start off with the base case. The base case is, well, we don't do anything with the current pixel that we're at. So let's just update that. Image ij is equal to base image ij, which is quite straightforward. And now we need to update all of these things. So I'm going to just put it in a loop because I don't want to write a million if statements. So for ij, I'm going to say ij, pretty sure that's what I just wrote anyway, and the fraction, or the error fraction in, and I'm just going to create a whole bunch of tuples. So 7 over 6 is we increase the width by 1 and we don't change the height. Go 7 over 16. And then the next one is negative 1 on 3 over 16. Right. And then 0, 1, 5 over 16. And then lastly we have 1, 1, 1 over 16, right? So 7 over 16 here, 3 over 16, which is negative 1, 1, 5 over 16, 0. So 0 was the same column, but we increased the row by 1. And then we move over by 1 and go down by 1, so that's 1 over 16 here. And here we update the pixel in the base image. If the particular offset is still within the valid image. So let's go and create, so this seems to be a, yeah, so let's create this. So I plus that's j plus j, which is the offset. Okay, and if they're all valid, so if this is greater than 0 and j is greater than 0 and I is less than w, yes, less than w, and j is less than h, well then we diffuse, we add the error diffusion to our image. Diffusion to our image. Okay, so this will be base image of ij okay, because this is the same, and then we need to add the error of ij, okay, times the fraction of the thing, which is the error fraction. And just for good measure, I'm going to clip the values to be between 0 and 1, because those are the legal values. And we should have a new image. So let's just have a look at what this image looks like first. The comparison already pre-written. some of this code. Quant image, recreate image. Run. Code is not defined, I think because it needs to be the code book. Okay. I think this takes a while to run, unfortunately. It's not as fast as this one because I haven't really optimized the algorithm. But you can see in the error, so this is the image with the error diffusion. Okay, this is original. This is the version with the diffusion. So you can see that there's some differences already. What's going on in this particular algorithm is we use this particular image on the right hand side as the basis for recreating this particular image in the middle. So rather than just returning the image, let's just do one better and recalculate the quantized image and return it. So this particular code is already in the scikit-learn workbook, so I'm not going to go through it. I encourage you to read it and think about it. Basically, there is a scikit built-in function called the Pairwise Distance argmin, which will allow us to do this, and when we can just recreate the image. And here we can see that even though the color space is exactly the same, there is noticeably more detail, at least from a subjective standpoint, in the picture on the right hand side versus the one in the middle. So that's pretty cool. Now what happens if we apply this to the one with the quantized palette? Now this is where we can run into a bit of interesting problems. So let's have a look. So that's k-means still. I don't want to use k-means, I wanted to use I have the code copied and pasted somewhere. Should be this one. I'm not mistaken. Oh, there we have it. We have the same version, but this time with the palette made from the 8 corners. And immediately we can see that, well, there are a whole bunch of colors that shouldn't exist. Yeah, we have all of these things that are not there. So what's going on here? Maybe we're being too overly eager with how we diffuse the error, and we are inadvertently adding new things that shouldn't exist. Maybe. So there are a few algorithms out there that do modified floyd-steinberg, so this color bleeding issue doesn't happen as often. But before we jump into that, let's have a look at Atkinson variation, which doesn't diffuse all of the error across, so hopefully it should do a bit better. This is a very minor change to the actual algorithm, so let's just copy and paste it, and all we have to do is change the actual weights in the middle. So this will be Atkinson, and what we're doing is, so 1 0, so this is all 1/8, and then it is 2 0 1/8, -1 1 1/8, and then 0 1 1/8, and then 1 1 1/8, and then finally 0 2 1/8. Okay, so these two, let's just line up these brackets properly. There you go. Did I line it up properly? No, I didn't. Here you go. So if asterisk is here, then we can go, there's 2 here. That's why this offset is 0. There's 3 values here, which is these 3 here, and then there's 1 at the bottom, which should be aligned with that one. So there we go. 0. So this is -1, 0, 1, 1, 2, and 0. And then these are the particular columns. There we go. And this would result in the Atkinson variation, and hopefully it won't be as severe in terms of a color bleed. Tuple not callable. Okay, I'm missing a comma. Right, there we have it. So we can see that already, if we just compare naively, there is less kind of noise, and let's be a little bit more explicit and just only compare the 2 here. Okay, the left hand side will be the original image, and then Floyd-Steinberg, and then the Atkinson variation. Now, of course, the Atkinson one, it may not necessarily be all that much better, but you can see, at least for the head, there is less color bleed, but there is certainly still a lot of color bleed on this wing and elsewhere. So this is some algorithms on error diffusion, which you can think about using. Now, all of these results look far better when you convert them to black and white, and I will show you very briefly what that looks like. Okay, so I think this is so we can see here, well, this is not a good example. That one, go. So this is a k-means variation. You can see that there's a far more detail. It looks much closer to the Wikipedia examples for this particular example, and also for this one, which is a quantized palette versus the k-means palette. This is a lot more detail. You can see in the middle of the body, and you can see, middle of the body again, and also the head. This is a lot more detail when you go into black and white, because you're not so affected by the random colors and the difference in contrast and so on. So there you have it. This is just a quick video on some dithering algorithms that use error diffusion, and it's just a subjective take on how the human eye perceives things, and how we overcome some of these limitations using some of these algorithms.